Okay, so we are back to our crypto cafe, and we have our very own William Youmans, who will talk to us about some exciting research that he did. So thank you very much, and the floor is yours.
Yeah. Yeah, so I'll be talking about solving the principal ideal problem with subfields. And this is joint work with myself, Jean-Francois Bias, Klaus Fieker, Tommy Hoffman, and a paper titled An Algorithm for Solving the Principal Ideal Problems with Subfields. And so just a brief outline of what we'll be talking about. So first, why do we care about this in cryptography? That this is the crypto cafe after all. So we'll talk about that, as well as some prior work that's been done for the principal ideal problem and some related work, and then our contributions. We'll also talk about, describe the algorithm for the principal ideal problem. We'll introduce a simplified case of multi-quadratic fields and some generalization of this idea into a concept known as normalization, some sub-problems that arise, like the problem of determining roots modular units, and then recap the algorithm. And then we'll discuss our results with a complexity analysis, some computational results. So first, the connection to cryptography. We'll start by talking about lattices. They're not going to be very prevalent in this talk, but it describes the connection very well. So a lattice, given n linearly independent vectors, b1 to bn, which we call a basis, where bi belong to r to the n, then we define a lattice as the integer linear combinations of b1 to bn. We call this a Euclidean lattice. We also define the minimum of the lattice as the length of the shortest vector. We call the minimum, or lambda1 of L. And for a lattice, we have here a lattice in Z2, and we have two bases for this lattice. On the left-hand side, we have a basis, two vectors, 0, 1, and 1, 0. On the right-hand side, we have a basis vectors 1, 1, and 2, 1. And you can see that the integer combinations of these do span the same lattice, all of the integer points of r squared. However, the left-hand basis looks a bit nicer. The basis vectors are orthogonal, and if you wanted to ask a question, for example, what's the shortest vector in this lattice, then a basis like we have on the left is a lot easier to work with than a basis like we have on the right, where the vectors are much more skewed. So why do we care about lattices in cryptography? Well, they're simple and efficient to implement and work with. They're also a good source of hard problems for that appear to be resistant to quantum computers, so they're interesting for post-quantum cryptography. And one of those hard problems is what we call the shortest vector problem, or SVP. The problem is to determine a vector in the lattice whose L2 norm, or length, is lambda1 of L, so it's a vector which achieves the minimum, or a shortest vector. And this can also be generalized to the gamma shortest vector problem, which we'll be talking about quite a bit. So here we just loosen the definition of a short vector. We want to find a vector of the lattice whose length is less than some factor, gamma times lambda1. We call gamma the approximation factor. So how hard is this problem, gamma SVP? So if we take gamma to just be 1, or approximation factor is 1, this is just exact SVP. The best algorithms that we have take time exponential in the dimension of the lattice with methods like sieving or enumeration. And of course, the discussion here can be a lot more nuanced. This is just an overview of the idea. And but if we take gamma to be polynomial in the dimension of the lattice, so slightly larger, then the best known algorithms like BKZ would take time still exponential in the dimension. But once we get to a sub-exponential approximation factor gamma, then methods like BKZ take time sub-exponential in the dimension, so a slight decrease. So we have these trade-offs between the gamma and the time complexity. And if we take gamma to just be exponential in the dimension, the time would be polynomial. And with methods like BKZ or LLL, which are BKZ and LLL are just lattice reduction techniques to find nice spaces. So for a small enough approximation factor gamma SVP is a reasonably hard problem. And it's for this reason it's used as a basis in many crypto systems. We won't talk about those really, but yeah, and also like we said, these problems do appear to be quantum resistant or resist quantum computers. So even given a quantum computer, these are still generally the best known techniques for solving these problems, gamma SVP. So why do we care about lattices? Where do ideals come into the picture? An ideal is a lattice. So we won't need this definition much, just to give you an idea of how an ideal is a lattice, though. We can use what we call the canonical or Minkowski embedding of an ideal, which is every field has embeddings, which sigma I into the complex numbers. And if we take an element of the field, we can map it to the vector of each of its embeddings into the complex numbers and their absolute value, which is a vector in R to the n. So an ideal of the maximal order of a field has a basis. And so we can do this for each of the basis elements, producing a bunch of vectors, which then we can take as a basis of a lattice. And why do we want to do this? Is because the algebraic structure that we have in a field also can be used to improve efficiency when working in this lattice. So, of course, a lattice is an additive abelian group, but when we an ideal lattice also has a multiplicative structure, so we can take advantage of that. And so there have been proposals that rely on the hardness of gamma SVP in an ideal lattice. In 2010, there's the homomorphic encryption scheme of Smart and Vercauteren. In 2013, the candidate multilinear maps of Gard, Gentry, and Halevi. In 2014, there's the British GCHQ proposal for a post-quantum secure encryption called Soliloquy. And all of these relied on the assumption that gamma SVP in this ideal lattice is at least as hard as gamma SVP in a general lattice or an arbitrary lattice. So now how does this relate to the principal ideal problem? So first we'll define this. This is obviously the problem that we're going to be focusing on for this talk. The principal ideal problem, or the PIP, is the problem of given a principal ideal, we wish to find a generator of it. And let's also define the mildly short vector problem, which I'll call MSVP. MSVP is just gamma SVP, but with a sub-exponential approximation factor of 2 to the O tilde, the square root n. And if you recall from that table, best known algorithms like BKZ would take time sub-exponential, in this case, time 2 to the O tilde square root n, to solve the mildly short vector problem in general. So any algorithm that can solve this problem better than BKZ would be interesting. It would show that if we're in an ideal lattice, then it's not quite as hard as a general lattice. So how does this MSVP problem relate to the PIP? So in principal ideals of a cyclotomic field, it was shown that there is an efficient reduction of the mildly short vector problem to the principal ideal problem. So if we can solve the PIP, then we can solve mildly short vector problem. And in general ideals of a cyclotomic field, we still have an efficient reduction, but it requires a quantum computer. So it's an efficient quantum reduction of MSVP to PIP. So the interest now is in solving the PIP in time, say, better than 2 to the O tilde square root n, which would give us a solution to MSVP that's asymptotically outperforms BKZ. So some prior work in this direction and discuss what's been done for the PIP. So the best known algorithms were for imaginary quadratic fields in the old days, pre-1989. And they took time exponential in the logarithm of the discriminant. The discriminant is a sort of invariant of a number field that we can use to quantify this complexity. The first sub-exponential time algorithm was given for imaginary quadratic fields by Hafner and McCurley in 1989. In 1990, extended to arbitrary number fields, but of fixed degree, so they can't be too large, by Buchmann. And in 2014, a heuristic sub-exponential algorithm was given for all classes of number fields due to Bias and Beaker. In 2016, a quantum polynomial time algorithm was described by Bias and Song. So if you remember on the previous slide, he said that MSVP has a quantum efficient quantum reduction to the PIP. Combine that with this last result, and we have that with a quantum computer in an ideal lattice in a cyclotomic field, we can solve MSVP in quantum polynomial time. And so this is interesting because, like I said at the start, with lattice problems, there are typically no known quantum algorithms that can outperform classical ones. So the other half of this talk is about subfield methods, how we can use these to improve the PIP algorithms. So in 2017, a recursive PIP algorithm was shown for multi-quadratic fields of this form by Bach, Bernstein, de Valence, Lange, and Van Bredenthal. And they found a super polynomial improvement over the sub-exponential methods for the PIP, the general ones, and even for certain engineered cases, a polynomial time algorithm for the PIP for these fields. In 2018, it was extended to S-unit group and class group computation by Bias and Van Bredenthal. And the S-unit group and class group we'll mention a little bit, but they're closely related to the PIP. In 2020, these ideas were extended to multi-cubic fields by LeSavary, Blanchard, and Cecilio. In 2020, this was then generalized about as far as it has been so far to the case of non-cyclic Galois number fields by Bias, Speaker, Hoffman, and Page. And so they gave algorithms for recursive S-unit group and class group computation using subfield methods that apply to any non-cyclic Galois number field. And in 2022, recursive S-unit group computation was used to solve the PIP by Bias, Langara, Beaker, Hoffman, and myself. And this is different from the work that I'm presenting today, and we'll discuss that a little bit. So the contribution here is to use subfields to solve the principal ideal problem, but we would like to avoid using S-unit groups. We'll explain why. And this can be done more efficiently than previously possible in certain families of fields. We provide an implementation in Julia that solved PIP instances in degree 400, 864, and 1800. These are much higher degrees than PIP has ever been solved in before. And we also provide complexity analysis and with family of fields where we have a good improvement. So to talk about the algorithm, just some quick notation. We have K, a Galois number field of degree n with discriminant delta K, ring of integers OK, which we also call the maximal order, invertible elements K times, the unit group OK times, the S unit group is written OKS times. And so the S unit group, we're only going to mention, we won't need really the definition, but if you're interested in it, it's here, which is that we have S as a finite set of prime ideals. The S unit group is just those elements, those invertible elements of K, which have valuation 0 at all the primes outside of S. So they're only divisible by primes belonging to the set S. And the unit group, the invertible elements of OK, are contained in the S unit group, and it's finitely generated abelian group. We also might mention the class group. We don't need the definition either, but here it is if you're interested. It is just the quotient of the multiplicative group of fractional ideals, modulo the principal fractional ideals. The trivial result of class field theory is that it's a finite abelian group. So we'll talk about multi-quadratics as a nice toy case to describe these subfield methods. So multi-quadratic field we already sort of showed is the rational numbers, the joined square root of d1 to dk, where the d sub I are integers, coprime, and square free. for this case, we'll just assume that K is 2, so we only have 2 square roots, and the field is degree 4. The Galois groups generated by elements sigma and tau, which have order 2. So the field K then has 3 degree 2 subfields. One, the field fixed by sigma, Q adjoint square root D1, the field fixed by tau, as well as the subfield fixed by sigma tau. So we can, so we have 3 subfields, all which are quadratic, and we can recursively apply this sort of subfield picture to multi-quadratic just by treating it as a biquadratic field and do this procedure recursively. But what's interesting is that when we have this type of Galois group, we also have this type of identity. For all the elements of the field, the invertible elements, alpha squared is the product of its relative norm down to these 3 subfields, K sigma, K tau, and K sigma tau, all over its absolute norm. So what you should get out of this equality is that squares of elements of K are just products of elements of subfields. So we can use this, for example, outline how to compute the unit or class group. Well, here just the unit group. So if we just take U to be all of the units of each of the subfields and lift them up to K, then U has to contain the squares of units, and it also is a subgroup of the unit group, which allows us to deduce that U must either, its index in the unit group must either be 1 or 2, meaning it's either the full unit group or it has index 2 in the unit group. Of course, if it's index 1, then we found the unit group and we have computed it, which is great. Otherwise, you have to do more work, which we'll talk about. Another brief outline of what we can do is, of course, solve the PIP. So if we take a principal ideal generated by an element alpha, we can solve the PIP in the subfields to find an element alpha, so I'll call it alpha sub sigma, such that this element alpha sub sigma generates the relative norm of our input ideal. So we take the relative norm of our input ideal, find a generator. We can combine this information using the equality that we had. And what we'll find is that this product of each of the generators of the relative norms all over the absolute norm is a generator for the square of our input ideal. If we want to find a generator for the input ideal itself, it takes more work. And again, we'll talk about that. So this concept was generalized, like I said, by the speaker, Hoffman and Page, to the concept of a normalization. And this definition here is a bit of a abusive notation. It's really a normalization. It's really it's totally determined by the Galois group, and it's a group theoretic definition. Here, we're going to just describe it in terms of field elements, which is just one application of it. So we say that a field K has a normalization if we have subgroups of the Galois group H sub I, as well as elements A sub I and B sub I belonging to the group ring and of the Galois group, and an integer D greater than 0, such that for any element of the field, we have this equality, this identity, that dth powers of field elements can be written as their relative norms down to these fixed fields with these exponents as well. So here, K cannot be cyclic. If K is cyclic, we will not have one of these identities, or at least not a non-trivial one. The elements of the group ring, when we write them as exponents like this is what we really need. It's not important, but it's there just in case you would like to know. We call D here the denominator of the normalization, and we call the AI and BI the coefficients. It seems a little weird, but like I said, the definition really is a group theoretic one. In that context, they really appear as a denominator and as coefficients. So that's why they have that name. And of course, if the denominator is equal to 1, then a lot of the problems we saw before go away. So we are interested in that case, of course. And when that does happen, we also have that the subfields, the fixed fields, also will have normalizations themselves. So we can sort of recursively apply this. Now, we can simplify things by assuming that K is an abelian field. In this case, we have an explicit formula that gives us an optimal normalization. So we don't have to search for one. By optimal, what we mean is the subfields have the smallest possible degree, and the denominator is also as small as possible. The coefficients AI and BI are now just integers, not elements of the group ring. We have a denominator P normalization if and only if the Galois group has a subgroup Z mod PZ squared for some prime P. And of course, this means that the Galois group is not cyclic. We have a denominator 1 normalization if and only if we have both a denominator P and a denominator Q normalization for two distinct primes P and Q. And the degree of the subfields is bounded by the size of the largest cyclic subgroup of the Galois group. So again, like the Galois group really totally determines this sort of what we get here. If we further assume that we're in a cyclotomic field, we can make a couple other notes, which is that we have a normalization if and only if the conductor is not 2, 4 p to the k or 2 times p to the k. These are exactly those conductors where the cyclotomic field would be cyclic, or p not equal to 2. And this is a density 1 subset of cyclotomic fields. So for almost all cyclotomic fields, we do have a normalization. And we can also bound the degree of the subfields by lambda of m, which is the Carmichael lambda function. So it's just a nice way that we can determine exactly the size of the subfields that will occur. So now let's revisit this biquadratic example. Like we said, we had this identity. This is our denominator 2 normalization. The subfields have degree less than or equal to 2. There's these quadratic subfields. So that was just an example of a normalization. In the multi-quadratic case, the Galois group is given by z mod 2z to the k power of degree 2 to the k. Here we have a denominator 2 to the k minus 1 normalization. And so any invertible element of the field, its 2 to the k minus 1th power can be written as a product of elements in the subfields ki. And these subfields, well, first I'll say that you could find this by just recursively applying that biquadratic example again before. But the interesting part here is that each of the subfields ki have just degree 2. So we can work in only degree 2 subfields if we use this normalization. And finally, a cyclotomic example. If we have conductor 63 cyclotomic field, this Galois group would be z mod 2z squared times z mod 3z squared. The degree is 36. And this will have, it has a denominator 2 and a denominator 3 normalization, hence it has a denominator 1 normalization. The subfields of this normalization all have degree at most 18. Each of these subfields then will also have a normalization of denominator 2 or 3 with subfields of degree at most 6. So we can reduce some computations here from degree 36 all the way down to degree 6, depending on what we're doing. So Bias, Speaker, Hoffman, and Page that gave this generalization as normalizations, they showed how you can compute the ring of integers from the ring of integers of subfields using a normalization. They showed how you can recursively compute the S-unit groups from the subfield S-unit groups. And S-unit groups can be used to compute the class group as well as the unit group itself. And they can also be used to solve the PIP. And they also were able to find a way to just compute the structure of the class group without computing generators. So it's a finite abelian group, and computing generators is usually what we mean when we say computing the class group. But if you're interested in just a structure, then we can do that with normalizations. And so I said that we can use the S-unit group computation to solve the PIP, but using the S-units to solve the PIP takes a lot of root computations. You have to take a lot of roots. And this is because if you imagine that we're lifting all of the S-units from a field from subfields to a top field, the normalization will have a denominator d exponent. So for each of the S-units, we have to take a dth root. So when we try to lift data from the subfields, we have to take these roots in order to learn about the field and not just its dth powers. And so if we try to solve the PIP using S units, we wind up having to do a lot of root computations. And these are add up a lot in practice, like we'll see at the end. So that's the motivation for this work. It's a different way of solving the PIP with these subfields that avoids S units. And then just to note this example, which is impressive, the speaker, Hoffman Page, in conductor 6,552, the field of degree 1,728, they're able to compute the structure of a class group in just 4.2 hours, which is far superior to any other methods out there for this type of field. So how can we use this to solve the PIP? So we've already outlined it a bit, but I'll outline it one more time just to really highlight the key problems that we have to solve. So if we have a denominator denormalization in the field, then we also have this identity for ideals of the field. So the normalization also applies to ideals, essentially. For any ideal, its dth power is relative norm of down to all the subfields occurring in the normalization. So this gives us our general procedure. We can find a generator for each of the relative norms. We want to find the beta such that it generates the relative norm of our input ideal with that exponent. Then what this means is that if we take a product of all of these beta I to the AIs, we find this element beta, which must be a generator for A to the D. So we can, like we outlined in the quadratic case, biquadratic case, it's not too hard to find a generator for A to the D. Now, the problem is we want a generator for A. So what we can do is search for a unit, U, such that U times beta is a dth power. If A is principal, then such an alpha must exist. So such a unit must exist. And this is a non-trivial problem that we'll discuss, an interesting problem that comes up here. So we would say here that we're searching for, we would say here that beta is a dth power modulo units. There's some unit such that the product is a dth power. And finally, once we have this unit, we have this alpha to the D, and so we can take a dth root of just this number field element to produce a generator for the original ideal. So the problems here are step 3, finding this unit, step 4, computing this root. And just keep in mind here that in step 2, for example, our generator beta was a product of beta i's to some exponents. We want to keep this in this factored form. We're not going to evaluate these products because that becomes very expensive. We store beta in the implementation as just the product of the beta i's. So we're only storing the beta i's. We never evaluate that product, and that becomes important when we just talk about discussing roots. So first, this problem of computing roots modulo units. To summarize that problem, given an element beta, we wish to find a unit such that U times beta is a dth power, if it exists. So the way that we can do this is the following theorem of Grunwald and Wang. This is a local global principle about dth powers. So if we let S be a finite set of prime ideals of the ring of integers, consider the canonical map from K invertible elements modulo dth powers into the product of KP, which is the completion of KFP, it's a local field, modulo dth powers in KP for all the primes not in S. So the idea to take away from this is that that we want to look at information in the completion, basically modulo, well, not modulo prime ideal, but local information in order to determine whether we have a dth power globally. So this map is either injective or is kernel of order 2, which is the theorem of Grunwald and Wang. And what this means is that if alpha is a dth power, or let's say alpha is a dth power, if and only if it's a dth power in each of the completions. That's all that this map means when it is injected. So this gives us the following idea of what we call saturation. So if we let U be a subgroup of the unit group, we could take it to be the full unit group if you want. But if it's a subgroup, it has to have index M co-prime to our denominator, and V will define as just U and beta. So we're taking essentially a bunch of units as well as our element beta that we're interested in. We compute the kernel of this map, which is to say that, well, I think the easiest thing is just to skip to the next line, which is that the intersection of the kernels of these maps will contain all the elements U times beta, such that U times beta is a dth power. So if we compute the intersection, then the intersection must contain some U times beta that answers our problem here. And you'll see the intersection is over the primes of norm less than or equal to C. And if we take this intersection for all of the primes up to this bound C, then the kernel will contain either exactly our solution or it will be empty. So this problem really just reduces to linear algebra, actually. And of course, I'm not going to explain this right now, but it's easy to do computationally. And that constant factor C guarantees that we have a finite runtime here. And in fact, under GRH, generalized Riemann hypothesis, it's polynomial time. In reality, we don't use this bound C because in fact, you can compute the intersection of these kernels for just a handful of primes, and that will generally be enough. So this gives us a way to solve our problem of finding a U times beta, which is a dth power. Now, there was that other problem I mentioned, which is the root computation. And the unit U that we have is going to be, well, a power product of units itself. But we also said that beta is going to be the product of beta i's from the subfield. So I said that we did not want to evaluate this product because it's very expensive. But then you have the problem of computing roots. How do you efficiently compute the dth root of some unevaluated product, say gamma I to the EI, if it exists? And the way we do this is with compact representation. And here I'm not going to explain really at all the inner workings of the algorithm, just the input and the output and what it can do. So if we have an unevaluated power product gamma, and where we know the factorization of all of the norm of the gamma i's, as well as an integer d, then compact representation will find that the sequence of elements alpha 0 to alpha k, which are reasonably small, such that gamma can be written as a power product of these elements. But notice here that the product is alpha 0 times alpha 1 to the d, alpha 2 to the d squared, and so on. So the powers are all powers of d. What this means is if we want to compute the root of dth root of gamma, all we need to do is compute the dth root of alpha 0, and we can just subtract 1 from the exponents of all the other terms. So we reduce this problem of trying to compute a dth root of some large power product, avoided having to evaluate it, and instead can compute the root of some reasonably small element. So this is how we circumvent those two problems. And now we can describe the general algorithm sort of again. So we'll talk about it again in this a cyclotomic example. If we have a cyclotomic field of conductor 63 with Galois group Z2, Z mod 2Z squared, Z mod 3Z squared, we said we have a denominator 1 normalization where the subfields have degree at most 18, a denominator 2 or 3 normalizations in each of these subfields, 2 subfields of degree at most 6. What this means for the algorithm is that we can reduce the principal ideal problem to the principal ideal problem in the Kij, the subfields of degree at most 6. And we then have to do a saturation, compact representations, and root computations in the subfields Ki that had degree at most 16. And here is just a general outline of the algorithm, but we have discussed it a few times already, but the idea is we just find the generators of the relative norms and subfields, and we can compute g of roots modulo the units to recover a generator. So let's talk about the complexity of this algorithm then. Up to polynomial factors, it's totally determined by the subfield cost. Resolving the principal ideal problem in a field that has a norm relation is going to take time, polynomial in some terms, like the log of the discriminant and the norm of your input and so on. Plus the cost, the PIP of subfields, which is the cost of the PIP in the subfields. So we said the principal ideal problem, our best known algorithms for this are sub-exponential. And so really that dominates the complexity here. And so that's why we say the complexity is totally determined by the cost of the PIP in the subfields. And if L is a subfield with the largest discriminant, then the cost of PIP in the subfields would be L, which is our number of subfields, times 2 to the O tilde log of delta to the 2/3. That's the complexity of the general algorithm for solving the PIP. And like I said, there's that algorithm for solving the PIP using S units, where we have more root computations in reality, but asymptotically, they're the same. They have the same complexity.
Do they have the same complexity also in the constant involved in the exponent there? Or maybe or feel that in that there are some extra log factors?
There may be, but there may be some difference in the polynomial factors potentially. Yeah, I'm not sure.
Isn't that what you have? Yeah, I mean, if there's some constant involved there, the exponent can make a big difference. Right? Even this is classical algorithm. This is convective is classical by both sides, right? Yeah. Well, this is the sub-exponential Gauss-Speaker algorithm. Oh, I see. Okay. Yes. But yeah, I suppose if you try to determine like the number of root computations, you could factor that into the complexity too, and then you'll see a difference in the complexity between the two algorithms. But generally, they have the same asymptotic complexity. And so the best known in cyclotomic fields, the best known algorithm for the PIP take time 2 to the O tilde the degree to the 1/2. And we can try to identify cyclotomic fields where we can achieve a complexity 2 to the O tilde degree to the epsilon, for some epsilon less than 1/2, aka we can try to find fields where we get a super polynomial improvement over the standard classical algorithm. And we could do this by sort of parameterizing the complexity of our algorithm. So we can, resolving the principal ideal problem in a cyclotomic field of conductor M, where lambda of M is, again, the upper bound on the smallest subfields, degree of the smallest subfield. If we assume it's less than or equal to 5m, the degree, to a power of a, for some a less than or equal to 1, then we can parameterize this complexity like this. It's going to be polynomial factors times 2 to the O tilde, the degree to the 2 to the a over 3, where lambda was that Carmichael lambda function. And so if a is less than 3/4, then we find that our complexity satisfies our goal. We have a complexity of 2 to the O tilde degree to the epsilon for epsilon less than 1/2, super polynomial improvement over the standard best known PIP algorithm. So when does this happen? How often do we have lambda of m less than or equal to 5m to the 3/4? So not too often. It's a density 0 subset of cyclotomic fields, but it actually in practice does happen quite often. So here we're looking at, I'll look at the first row in the first column. This is the number of cyclotomic fields of conductor less than 1000, where we have this property is true.
and we have our super polynomial improvement. So this occurs for 30.2%, 20% of cyclotomic fields in this range. And if we increase the range up to even 100,000 in the third row, the percent of cyclotomic fields where we have this improvement is 26.32%. So in a sort of practical range of conductors, we have about a minimum of 25% cyclotomic fields where we have improvements of the standard algorithm. And then we can, of course, in the following columns, try to reduce the degree of the subfields even more, and we see that it becomes less and less frequent, of course. And one more sort of note about this complexity is that the following theorem of Erdos, Pomerantz, and Schutz says that there exists an infinite sequence of positive integers on 1 and 2 and so on, where their Carmichael lambda function of those conductors n sub k is in log of m sub k to the big O of log m sub k. What this means is that for these conductors, our algorithm would have complexity in 2 to the degree to the little o of 1 in this family of fields. So finally, the computational results, he advertised that degree 1800 field. So we can sort of skip to that result in this table here. So the third row of this table, K3, we describe the field. So this is a field of conductor 2387 of degree 1800. It has 131 subfields in its normalization and all of degree at most 150. These all have normalizations going down to 297 subfields of degree at most 30. So PIP reduces to degree 30. Saturation of root computation is done in degree 150. And some timing for the resolving the PIP instance in these fields. Again, I'll skip to just the third row in K3. So it took a total of 2,905 CPU hours. And the interesting thing about this, the runtime, so I described some of the details of the steps that are sort of the most interesting. In step 5, it's the time to compute relative norms down to subfields. Took a non-trivial amount of time here, 22.1%. In step 6, that was the time to compute for the PIP and all of the subfields. That only took 7% of the total runtime. And in step 9, the root computations in those degree 150 fields took a total of 56% of the runtime. So that's why we're so interested in trying to solve the PIP without S units to reduce the number of root computations necessary, because it's difficult in practice. One of the bottlenecks in practice. And that's it. Yeah.
Question is the last table time is measured as the CPU hours. So I want to know those time is the real time or estimation of the algorithm.
I believe it's the real time. I guess what you call the wall clock time, maybe.
So that means you're running that algorithm for like 2,000 hours.
So I guess that really is a point that I really should have stressed. One of the reasons that we're happy with having so many subfields is this is all done in parallel. So we do all these, say here, we're doing 150 root computations in parallel. If you add all the times together, then you get, this is the total time across all the cores added together.
How many computers you use to create a?
This was 150-ish nodes, I believe. Yeah.
You had a slide had a intersection time and fell under the function to analyze framework. I was just wondering why was the time only and why that is it a polynomial time? What kind of polynomial?
That was up here. Yeah. So what was your question here? Sorry.
So I just wondering, one, why are those, you're only taking the norm of the prime? Why is that?
Why are we?
Like, or some intuitions why that is? I know you said you weren't gonna like go through that, but.
Yeah, so, no, it's just that we, if you look at the previous theorem here, the Bruno rank theorem, here, there's no assumption on the primes. You can avoid a finite set of primes, but in general, to say that your df power, if and only if your df power in each of the completions, you would have to check every prime ideal. And to be sure, but that's not what we want to do. So this is a sort of effective version of this, where you can find a particular bound that says if you check at least all of the primes below this bound, then you're good. And we use the norm for that reason.
So how do you do that in algorithm? Do you pick up do you enumerate all the set of the prime key bounded by some norm, or you just pick up some random small?
So yeah, so we just pick a handful of I think we picked some large primes. I forget the reasoning for large or small prime, but just a handful of primes, and that's enough. Then we can look at the intersection of this kernel, and it tends to be that it already only contains solutions. Yeah, but to guarantee a solution, you have to check all of the primes.
They shoot very quickly somehow. You
Sorry?
they shoot very quickly.
Yes.
In practice.
Yes.
If you could have okay.
Yeah. That's like I don't think I put it on in the timings here, but I think it was 6 is the cost of PFP. I think in step 7 was the cost of saturation, and 0.1% of the time. Yeah, very efficient.
So GRH is just to allow you to theoretically bound into the account.
Yeah.
And what if you do something like probabilistic argument and can get rid of GRH?
I don't know. I would guess that there's something you can do to make it unconditional, find some unconditional bound. The bound might not allow you to argue a polynomial runtime. I'm not sure. Yeah, I'm really not sure though. Anyone else? Okay.
Okay.
Thank you.
Any question from the audience, maybe? Yeah.
Oh.
I don't think we have anybody. Okay, so thank you. Okay, so if no question, then we're going to stop here. Thank you very much all for participating, and so we'll reconvene again in 2 weeks.